Okay, everyone. My name is Alex Graves. I'm a research scientist at DeepMind, which should no longer say Google DeepMind, but only DeepMind, but I haven't updated my slides, obviously. And what I'm going to be talking about in this lecture is attention and memory and how we use these concepts in deep learning systems. So just to get started, I think it should be fairly, clear to everyone that attention and memory are important features of human cognition. And so, at the simplest level, what do I mean by attention? I mean the ability to focus on one thing and ignore others. So to be selective about what you're looking at, or thinking about, or listening to, or in some way giving, mental kind of bandwidth towards. So an obvious example of where we apply attention in our day-to-day lives is what's known as the cocktail party problem. In a room like this one was, 2 minutes ago, where everyone was talking at once, you can still pick out one person talking and ignore the others. So it's pretty clear we've got, we're using some form of at least sensory attention on a day-to-day basis. But then if you take it a little bit further than that, you can say, well, it's not just about, being able to pick out one piece of, sensory information, one piece of vision, or one piece of sound. It's also about pursuing one thought at a time, or remembering one event rather than all events. And so this, to me, attention is kind of intimately bound up with memory. Memory is something like attention over time. So, it's something people often kind of comment on is that, on the face of it, computers have a much better memory than people, right? We can store everything practically on a little memory key these days. We can put terabytes of information in a very small space. But when we talk about human memory, that's not really what we mean. We don't mean storing everything at once and accessing everything at once. We mean rather this ability to select salient information and attend to that. So for me, this is why I'm going to kind of talk about attention and memory together in this talk. Okay, so I'm sure you've all heard lots about neural networks in the earlier lectures that you've had. Just very briefly recap, what are they? Well, in purely sort of mathematical terms, they're parametric nonlinear function approximators that you can fit to learn functions that go from input vectors. So for example, a photograph might be represented as an input vector. An audio sequence might be a sequence of input vectors, a piece of text likewise. And you take these input vectors and you transform them into output vectors via this parametric function. And for an example, in the example we're looking at here, when you're doing image classification, this is from the ImageNet database. Your input vector represents a photograph, and your output vector represents a distribution over class labels. In other words, it represents the probabilities that you're giving to the labels that have been applied to this class. So in this case, the computer thinks it's probably a leopard, but it might be a jaguar, or maybe a cheetah, or a snow leopard, or an Egyptian cat. And at first glance, this doesn't have a whole lot to do with attention, right? You feed in a whole vector and you get a whole vector out. It appears that the network basically is just looking at this whole picture. You've already, in some sense, it feels like we've done the attention for the computer beforehand by picking out this picture of a leopard. And from there on, it's just, straightforward function approximation. But actually, if you kind of peek under the hood a little bit into these neural networks, you see that within this parametric function that they're learning, there's a kind of implicit attention, meaning that they respond more strongly to some parts of the data than others. So going back here, the network might be particularly attuned to, for example, the spots on the fur here, right? Because that's something that discriminates, a leopard from, for example, a snow leopard. It might also be looking at things like ears and eyes, because those are things that tell it that it's looking at an animal and not a tree or something like that. And to a first approximation, we can get a handle on where this attention is being focused by looking at the network Jacobian. So if you're familiar, this is a standard term from linear algebra, linear analysis. You basically just take the sensitivity of the network outputs with respect to the input. So by design, these neural networks are differentiable function approximators because we train them all with gradient descent. We use the backpropagation algorithm to find the gradient. And we can use this same algorithm to give us the Jacobian. That is to tell us when it predicts an output like leopard, what parts of the image was that decision most strongly conditioned on? What was it really responding to? What made it think that this was a leopard? And here's just a little illustration of what that is. If y is your output vector and x is your input vector, you get this dyi by dxj. And you basically get this, if you've played around with backprop, it's very straightforward. All you do is, instead of setting the errors to be the gradient of the loss with respect to the outputs like you would normally, you rather just set them to be the output activations themselves and then backpropagate that. And here's a little illustration of this visualizing this Jacobian in action in a neural network. And this is a somewhat complex neural network system that kind of, I think, ties in nicely with what you will have been learning about in parallel, which is deep reinforcement learning. So reinforcement learning using deep neural networks. And this particular neural network has it's an interesting one. So it takes the video input at the bottom of this stack and then passes it through a layer of convolutional neural networks, which are the standard neural networks for dealing with image data. That learn these kind of this pyramid of local filters applied to the image, transforming it into some higher level representation that can be used to make decisions like how to act, for example. So this is a system that is being trained, I think in this case it's being trained on Atari games. It's getting video streams as input, and it has to choose the actions that it should take as output. But unlike most of the deep neural networks applied to Atari, this one has what we call two heads. It has two sets of outputs. One of them basically tries to model the value of the current state, and the other one attempts to model what we call the advantage of taking a particular action, the action advantage, which basically says how much better, so I have a notion of how much reward I expect to get in this state, full stop. So you're looking at a screen in Atari and you think, okay, I'm probably going to get another 50 points in this game, just on average. But then you also have a notion that some actions you could take right now will be better than others. And that discrepancy is the advantage. And the reason they split this up into two heads is that these two, you can model these two things together, and that's actually the normal way of doing it with a single set of outputs. But they're on very different scales typically. Like the state value might have a very wide range, and the advantage of taking one particular action over another tends to be quite small. And so they found there was a great benefit in splitting them up. But what was really interesting from our point of view, or from the point of view of this lecture, is that they then visualized on this video here what the sensitivity of the corresponding outputs were to the video inputs received by the network. So on the left, we have the thing predicting state value, and on the right, we have the thing attempting to predict advantage. And the red kind of clouds that you see appearing are the degree of sensitivity. So they've superimposed this red heat map, and where it's really bright red, that means the network is very sensitive to what it's that particular part of the screen. And so if you look at, first of all, you can see that there's much more red on the left than on the right. So what this kind of tells you is that it's using a lot more of the information on the screen to assess the value of the current state than it is to assess the advantage of one action over another. And one thing that's very noticeable about the one on the left is always focused on the score. You see the score ticking over at the bottom. And so obviously the score itself is a very strong indicator of how much more score you expect to get in the future, right? If you have a notion of how much score you get on average full stop, then you can sort of subtract the current score from that to get a prediction of where you're going in the future. And another thing is you can see from this, the way this red flares up, that it tends to look quite far down the track, because in this particular game you get points every time you overtake another car. So it's kind of looking ahead and saying, look, how many cars are there in the immediate future that I'm likely to overtake and therefore get some score, some value for this state. I should point out, with all of these algorithms, there's a kind of exponential future decay of future rewards. So you're mostly focused on the immediate rewards you're likely to get rather than the ones in the very distant future. The thing on the right, on the other hand, only flares up very rarely, and it flares up when there's another car very close to it. And the reason for that is it's only at those points that there's really a significant difference between taking one action and another. So most of the time you'll do just fine driving straight and not doing anything. It doesn't really matter if you go left or right. If there's a car right in front of you and slightly to the left, suddenly it becomes very important whether you go right or left. Because if you go left, you'll bang into the back of it, and if you go right, you'll get ahead. And so this is just like a nice little illustration of what you can see is going on inside the network in terms of how it's implicitly attending to different parts of the screen without any kind of explicit attention mechanism. So nothing in this network, in this system, was trained to attend to one thing and not another. That's just a feature of these neural networks. And the same thing happens with recurrent neural networks. Now, recurrent neural networks are kind of my own speciality. That's where what I've done most of my research on over the past 15 or 16 years. And I focused a lot, in particular, on things like speech signals and language signals and sequences of handwriting, which I'll show in a minute. Now, in this case, so I'm assuming, have you heard about recurrent neural networks earlier on in this course? Okay, so I won't need to labor the point here. It's as you probably know by now, it's not so different from a normal neural network, except that you have these feedback connections. So you have a large parametric function that transforms inputs into outputs, but this parametric function is itself conditioned on its own internal state at the previous time step. And the overall effect of this is that you can think of it as something that transforms input sequences into output sequences instead of doing this one-to-one map from vectors. And to put it in more colloquial terms, what that means is that a recurrent neural network has a memory. It has a memory of past events which is encoded in this internal state. And so if you think about this attention thing again, it should be clear that once again the network will attend to some parts of this internal state more than others. And since that internal state corresponds to a memory of past events, what you can see is that it's got a kind of selective memory, right? It's selectively looking at some things and not others that it received in the past and using those to make decisions. And this is why I say that attention and memory are so kind of intimately bound up together. And so again, we can look at the Jacobian of this system. I call it the sequential Jacobian, just to distinguish it from the ordinary case. And what you're really looking at there is for any particular output at a particular time, which inputs over the whole input sequence was that output most sensitive to. So what if it made a decision at time t, which input at some time less than t most strongly influenced that decision? That's the thing that it's remembering, that it's recalling when it makes that decision. Okay, and this basically reiterates what I just said, but there's a little example here. So this is one of the first things that I really successfully applied these sorts of networks to was online handwriting recognition. And online handwriting basically means that you've got the trajectory of XY coordinates of the pen. So for example, someone writing on a tablet, or in this case it was a whiteboard that had an infrared tracker for the pen. And basically the data in that form is a lot easier to process than if you just get an image of handwritten text, right? Because you've got this nice, clean, low-dimensional representation that tells you how the pen moved as they wrote it. And that so the thing that they wrote is these two words, once having. The actual network inputs are represented the next line up. Basically, there's an X and a Y. There's a time input, which isn't very interesting. It essentially just monotonically increases. There was some variance in the time delays between ticks. And then there's this end of stroke, which shows where they lift the pen off the paper. In this case, they lifted up the pen after they wrote the letter O, after they finished the word once, and then again, right at the end, they wrote having all in one go, and then they went back and put a dot on the I. And this dot on the I is significant because from the network's point of view, that dot is extremely discriminative. When you're trying to recognize a letter I and say distinguish it from a letter L, it's the dot that really tells you that this is an I. And the point that was interesting about this data from a perspective of memory and of attention is that the dot, as far as the input sequence that was presented to the network, the main body of the I and the dot were quite far apart from one another, right? The I came in the middle of the stroke for the word having, the dot came right at the end. And so by looking at this sequential Jacobian so I looked at it calculated it at the point when the I was emitted. So the point when the network decided it had seen an I, or I should say this recurrent neural network is bidirectional. So there's actually two RNNs going in both directions. So it means that it has future context as well as past context. But just think of it as something that is mapping from the entire input sequence to the entire output sequence. And at the point when it emitted the I wanted to calculate, so what was it responding to when it made that decision? And you can see this blue line here shows the degree of sensitivity to the inputs that helped it make that decision. And you can see that it's much more sensitive to stuff at the end. Actually, what it's really responding to is the suffix ing. So actually, that whole suffix is also very discriminative, right? Like that, because that's a common suffix, if you see an N and a G immediately after a letter, you already have a strong kind of prior that it's an I and not an L, right? Because LNG is not a suffix and ING is. And then there's this little spike right at the end of sensitivity, and that spike corresponds to the point where the dot was placed. And so I thought this was, this really excited me at the time because it showed how kind of intricate the underlying mechanisms that these systems were learning actually were, right? They weren't just somehow like taking the whole input sequence and putting it in a bag and pulling out an output. They had this complicated selective attention mechanism that was learning to ignore some things and attend to others. And again, as I say, this is closely bound up with the idea of having a selective memory.
Sorry, the Jacobian here, is it just for the output of I?
Yes. So I calculated just for the single unit corresponding to the I at a particular time point. So I think what I actually fed back into the network was a network, a one-hot vector, like all zeros and a 1 for I, and then backpropagated that. You have to be careful because if you try to backpropagate with respect to the entire softmax, you always get 0, right? Because the entire softmax always sums to 1. It's normalized. So you have to be a little bit, aware of that. Okay, and here's a video of the same thing happening in real time. So the user is writing the words appearing on the second from bottom line. The internal state of the network is shown in the second top row. I mean, interpret it as you will. The decisions made by the network are at the top. So you can see when it's deciding to output letters. This is a unidirectional network, so it only has past context, which means it has to kind of wait until it's finished a word before it makes a decision. This ghostly thing at the bottom is the sensitivity of the network. Maybe just play that again. You can see, as it rolls on, it's responding mostly to the recent past, but, it also looks back to previous words and previous kind of clusters of letters to help it understand what's going on now. But, the point is it's not uniform, right? It's not uniformly looking at everything it's seen so far. It's selecting out certain things that help it to make decisions. And you can do even more than this with implicit attention. You can do things like reordering in machine translation. So for example, it's a big problem of translation between English, for example, and German, in that German verbs tend to end up at the end of sentences, and this creates problems for automatic translation systems because they have to take them and reorder them. And in this case, oh God, I used to know a little bit of German because I lived there and I've forgotten it all, but the zu erreichen at the end here corresponds to reach, right? Which is right at the beginning. Is there any German speakers here? Yeah, is that right?
Zu erreichen, yeah.
Yeah, thank you. And so the network, you can see that the network has to basically take this thing at the end and move it back to the start. And by looking at, again, another form of Jacobian, you get this matrix that says, well, which input, basically the columns, the things on the left, I think, the vertical dimension is the input, so the rows are the inputs, and the columns are the outputs, I think. Actually, it doesn't really matter which way around it goes. But the point is, you can see, if you take zu erreichen at the end and look up through the rows, you can see that it's mostly sensitive to this word reach at the start, right? And so, like, this is sort of interesting in that it's not just this is being done by passing the whole input sequence through a very deep convolutional network. So there actually isn't even an RNN in here. There's just a lot of convolutional layers, and even with a system like that, it's able to kind of successively pass this information around and reorganize it so that something at the end of one sentence becomes, the main discriminative feature for something at the beginning of the other. So again, it's not just kind of forgetting some things and remembering others. You can use attention to reshuffle or reorder data as well. Okay, so what I've talked about so far are these implicit attention mechanisms that just kind of fall out automatically of having a neural network, of having a large parametric system. these are very interesting. It's nice to see these things there, and it's certainly worth analyzing them. But it feels like, at least in human cognition, we have a little bit more control than that. We have a sort of explicit attention. So, I mean, at the very least, you can see, just by moving your eyes towards a different part of the same scene, you're shifting your attention. And even internally, you can decide to concentrate on one thing or another. So it feels that not everything is done with these kind of implicit attention mechanisms. There are sometimes explicit ways that we decide to focus on one thing and not another. And there's several advantages to this. One of them can be computational efficiency. So if you can explicitly limit yourself to some subset of the data, then you don't have to reprocess the whole thing, right? And so you can save yourself time. Another thing can be scalability. So for example, if you've got a fixed size glimpse, you have a model of a kind of robotic eye looking at an image, then you can give it any size of image, any size of scene, while keeping the dimensions of the glimpses itself, the things that are going to be processed by your network, fixed. Another thing that I find very interesting is that you can turn static data into sequential data. So when I first started in machine learning, everyone was doing the opposite. Everyone would take sequences and kind of chuck everything together into a big bag and process it like a static vector, because people didn't really know how to handle sequences very well. Recurrent neural networks didn't work very well at that time. There was a strong trend towards getting everything into a single vector and feeding it into a support vector machine or something like that. And now in recent years, it's kind of going the other way. People are trying to turn everything into sequences because they found that these sequence processing models are so powerful. And so one example of that is if you've got explicit attention, you can turn static data into a sequence. You have a fixed photograph, but your eye moves around. So maybe you've seen these videos of how visualizations of how people look at images, these saccades of the eye moving rapidly. What you're actually getting in your brain is a sequence of very low kind of bandwidth fixations, rather than getting many megapixels at once, which is how we tend to think about these things. And I guess the last advantage of explicit attention mechanisms is that they can be much easier to interpret for the person running the experiment, as in easier to visualize, because you can explicitly see what part of the data this thing was focusing on, rather than having to do what we saw in the previous few slides and calculate some indirect measure like the sensitivity in order to work out where you were looking. Okay, so there's a whole bunch of neural attention models, and that's what I guess the rest of this lecture is mostly going to cover. But they all have a kind of a similar format. So you have a neural network that receives input and produces output as usual. So the bit with the gray lines here on the right of the image, you've got input vectors coming into a network that produces output vectors. The network might be recurrent, it might be feed-forward. It actually doesn't matter so much in this case. But there's also some extra set of outputs coming from the network that are used to parameterize an attention model. So for example, these might give the location of a gaze of the network, or it might give a time or a lookup key telling it what to attend to out of some a set of past data. We'll talk more about those specifically later. And then the attention model has some extra data to operate on. So this could be just the rest of the same image that you're looking at, or it could be another image, it could be an audio sample, it could be some text to be translated. But whatever it's looking at, it's going to take this attention model and somehow apply it to the extra data and create typically what it does, it creates some fixed-sized glimpse. This glimpse vector is then the thing that is passed into the network. So you've got just to recap, the network outputs some parameters. Those parameters are used to parameterize an attention model. The attention model is applied to some extra data. That gives you some glimpse vector of pre-specified size and format, and that's then fed into the network. And so an important thing to note is that the combined system here is recurrent even if the network isn't. So because you've got this loop where you output some attention parameters, and those attention parameters then affect what you will get as input at the next step, you've got something that is effectively recurrent even if the network itself doesn't have a recurrent internal state. Okay, so the general idea is to think of this probabilistically and say, okay, what we've got is a probability distribution over glimpses of the data. So we've got this extra data X, and we're applying our attention model to it using some set of attention outputs. So these attention parameters are called A here, right? And then so we get a conditional probability distribution, which is the probability of glimpse G given attention A, right? And the simplest thing you can do then is just say, well, A just assigns probabilities to a set of discrete glimpses. So if we imagine in this kind of cartoon picture here, there's 9 possible places we're allowed to look in this picture. Our parameters of our attention is just 9 numbers that we feed into a softmax and get a probability distribution that tells us which of these things we're most likely to look at. And then we sample from that, and that's where we get our next glimpse from. So this would be pretty much the simplest attention model you could have. And so if you do this, you can literally implement and use this. You basically treat the distribution over glimpses as a stochastic policy, right? So you've got this probability of looking here or looking there, and you think of this as a reinforcement learning problem. It feels a little bit different from normal reinforcement learning in that you're not actually modifying the environment, but you're modifying the information you'll get back from the environment. So from the perspective of the agent, from the perspective of the model, it's as if you've modified something in the environment. Does that make sense to everyone? Just by choosing where to look, you're already kind of implicitly changing your own environment. And so it becomes a lot like an RL problem, and then you can use RL techniques. If you say there's some reward, in this case, let's say it's the loss for something like classification that is induced by a particular glimpse, then you can use that to train the model with reinforce or some similar problem. And this is a general technique that's useful to know. Anytime you have, even if you have a supervised task, if you have some part of the system that's just completely non-differentiable, like as in you're going to look here or you're going to look there, and there's no, continuity between those things, there's no way of getting a gradient between one and the other, then you can sort of fall back on these RL methods. You can always use reinforce, basically, to get a stochastic gradient, even if you can't get a normal backprop gradient. But generally, you want to do something a little bit more complex than that. You wouldn't want to just have a softmax. You might have something like a Gaussian filter that has a particular center, the coordinates of its center. It has a width and its height. That is the distribution would be something more complex. Like there might be a continuum of places where you're going to look rather than a set of n discrete disjoint subsets. And also, usually the glimpses are going to be something more complex than just an image tile. So people build, quite sophisticated foveal type models where you have higher resolution in the middle and lower resolution out at the edge, so that you can, you can look at something, you can be focused on someone's eyes and get them in very sharply in high resolution, but also get the background of the scene at lower resolution because that might be useful for whatever decision you're making. And it also is useful to tell you where to look next, right? So like, in order to decide what to focus on, you have to have some kind of information about what's over there. You need to see a blur of something happening over there before you turn your head and look. And here's an example of something with a foveal glimpse model. I'm actually struggling to remember some of these papers. This is only 4 years ago, but it seems like a long time. This is from Recurrent Models of Visual Attention. And this was something that had it was allowed to output a sequence of glimpses while it attempted to classify an image. So that the model was foveal. Both of these two rows here, the thing on the left shows you the actual image and shows you the green points show you the fixations of the model as it processed that image. And then the remaining images show you the 6 things that the model actually saw, like what did it actually get back from this foveal image. And you can see that what it sees is some part of the image quite sharply, and other parts that are further away from the center are more blurred because of this multi-resolution model that's there. And really what's happening is that it's learning quite quickly to zoom in, and so the job here is to classify the images. This is just good old standard MNIST with some background clutter added so as to make it a more interesting attention type task. Because in normal MNIST, the attention is trivial. You always just look right at the center of the image, and there's no distractors or anything like that. So in this case, it learns to basically zoom in on the thing of interest, the number, and it learns to kind of go around it. Like you can see this very clearly with the 8. In its budget of 6 glimpses that it's got to recognize this thing, it uses them to kind of go around the perimeter and therefore get all of the important discriminative information it can before it makes its decision about what digit it is. And this was all trained with reinforcement learning. And here's an extension of this to identifying multiple objects. And sorry, this video goes a little bit too fast for, for me to keep up with here. So here we have basically the same data set, only with, I'll just go back to the start. The same data set, only with multiple characters in it instead of one, right? And this illustrates a sort of an example of attention straight away, actually, right? Like if you have a model that is, this is sort of comes back to this idea of turning images into sequences, right? If your images contain exactly one handwritten letter, and you can very simply define a kind of static classification task, you're always going to get an image in and you output a single class. If they contain a variable number of letters, it becomes harder to do that. It's much more natural to think of it as a sequence where you keep looking through the image, and every time you see another number that you didn't see before, you say, okay, I've seen one. And so in that sense, you can immediately see that this is, you have more flexibility once you think of the data as a sequence of glimpses rather than as a static image. Oops. Okay, I'll just let the whole thing run through. I think after this, it looks at some street view house numbers. And you can, basically what the point of this is, you can see it focusing. You can see it looking at one image, jumps from one number to another. It's using this fovea to kind of look in the periphery and then move out to see where it needs to look next. Here it has a whole sequence. It goes through them. It needs to go through them in order, I think, from left to right in this case. So it's learned how to do this kind of pass through things. I think in this case, it just, so first task, it just had to find the first digit. And these are like real photographs of street numbers. And here it has to read the whole thing. And you can see, again, it's learning to do these kind of sweeps, these passes through it. And I think it was also applied to ImageNet. So like, is it advantageous? So I mean, for classification where, there really is just a single target in a single image, there's usually not that big of an advantage to turning it, to thinking of it as a series of fixations, right? You're as well just feeding it into one big convnet. It becomes more beneficial to have explicit attention mechanisms when the tasks get more complex. How am I doing for time, by the way? Anyone? I should have my watch.
20 more minutes until 3.
Okay, and the break is at 3, is that right? So I think I'm actually a little bit ahead of schedule here. Okay, so these attentions we looked at so far used what we call hard attention. So there were these fixed attention windows that were trained with RL techniques. And the significance of this is that basically they're not differentiable. There wasn't a gradient that we could backprop through. There was a notion of you either look here or you look there. There wasn't a continuum between looking here and there. Now, for some systems, that's really necessary. Like if you've got a robot that has to choose to look left or look right, you're kind of forced to use RL, right? Because you're not going to get a smooth gradient between going to one and the other in general. But if you're just talking about, processing an image where you have the entire image on your computer, that's not necessarily the case, right? The attention doesn't really need to be hard. We just want to focus more on some regions and less on others. So something a little bit, in a way, more like the implicit attention we saw earlier. And if you do this in a differentiable way, what you end up with is what we call soft attention. And the point there is that soft attention can be trained end-to-end with backprop. You can train it just like a normal system. And generally, this is a lot easier than using RL. But on the downside, it can be more expensive to compute, because typically, with the soft attention, rather than selectively taking some little chunk of the image and throwing away the rest, you're still processing the whole. You still have to process all of the data at once in order to calculate this attention model. And just to give a little bit more detail about what the template of this is. So once again, think about it as a probability distribution over glimpses. So we've got a set of parameters A and a distribution over the possible glimpses G. But what we do now, in order to make it soft, is we take an expectation instead of a sample. That's really the only difference, right? So if you stochastically pick samples from this distribution, then the best you can get is a stochastic reinforced style gradient. If you take the expectation, on the other hand, and so if your vector G is now this weighted sum where you weight over the possible glimpses times the probability of that glimpse under your distribution that you get from A, then you directly can differentiate that with respect to A. You get a gradient with respect to your attention parameters. And those are the things that actually came out of the network. So you have a gradient flowing back into the network as usual. And this is used really there's all kinds of variants of soft attention, but they pretty much always come back to this basic template. It's just about taking a mean instead of a sample. And so at least my own first experience of using soft attention was when I was looking at generating. So as I said earlier on, I'd been looking at handwriting recognition, so recognizing sequences of online handwriting. And then I thought it would be interesting to look at generating sequences of online handwriting, and specifically to do handwriting synthesis, which means given some text sequence, basically write that sequence by hand, right? Generate a handwriting sequence from which you can read the text sequence that you were trying to generate. So basically just like text-to-speech, only it's text-to-handwriting. And to do this, I found that I needed an attention mechanism, because generally a text sequence might be a sequence of maybe 50 characters or something like that. It's a sentence that you're writing. But typically, the handwriting sequence would be much longer than that, right? Because this handwriting sequence was encoded as a series of XY points. And you might have maybe 10 or 12 points per letter, or more even. Depends on how big the handwriting was and how slowly they moved the pen and so forth. And it's highly variable how many points there are per letter. Obviously, like an H will typically take more points than an L, for example. And all of this meant that it wasn't straightforward to align these two sequences, right? I wanted a map from a text sequence to a handwriting sequence, but there was an alignment problem. And this is the same problem that you get in speech recognition and in text-to-speech and in other areas as well, where you need to kind of warp, you need to stretch and shrink these sequences so that they line up with one another. And there are various techniques for doing that, but one thing that I thought would be really interesting and really general is just to give the network a way of choosing what to attend to in the input sequence. And the way I did this, and I apologize, this slide isn't really very clear. The network basically outputs a bunch of parameters that parameterize a Gaussian mixture. So a set of weights, a set of means, a set of variances. And those things are then convolved with the input sequence that represents the text. So the text is represented as a sequence of one-hot vectors, this thing at the bottom. And then you have these Gaussians, which basically have means, so the means and the variance correspond to the position within the sequence. If you imagine that these things are indexed left to right, there's the 0th vector, the 1st, 2nd, 3rd, 4th, and so on, then basically what you're saying is the parameters of the Gaussian say something like, well, I want you to look at the 3rd element of the text sequence with some variance, maybe plus or minus 2 characters surrounding it, right? And then essentially, mathematically, all that's done is you convolve those Gaussians. So you just calculate the height of the Gaussian at each particular index along the sequence and multiply it by that one-hot vector, and then sum the whole thing together. And what you get is a kind of munged together vector that is more or less focused on different parts of this text sequence. And I apologize if that's a little bit hard to digest. You should look at the paper if you want this, yes, in more detail.
Were the number of components fixed?
Yes, the number of components was fixed. And one other thing I should say that's very important is it didn't output absolute numbers, but rather offsets from where it was looking at previously. So it was strongly biased towards the fact that both the handwriting sequence and the text sequence are going left to right, or right to left if you're doing Arabic. I mean, that part's not so important, but there's a continuum in that you're not doing this reordering thing that you are, for example, in translation. You're starting at one end and going forwards. And so, first of all, this worked very well. These are all generated sequence. There's an online demo. I think it's still working. If you search for my name, search for Alex Graves handwriting, you'll find a demo where you can type in some text and it will write it for you. And you can either let it pick a random style to write in, so it's learned these styles from the training set, or you can condition it by giving it a particular style and get it to write like that. Well, I've said real people write this badly. Maybe they don't write quite that badly. You know, like at its best, the sequence, this thing generates text that looks very much like real and somewhat messy handwriting. Sometimes it goes completely AWOL. But I think what's really nice is that it tends to pick a style and stay with the style. So from a generative modeling point of view, this thing's interesting. From the perspective of this lecture, I guess what's mostly interesting about it is that it was using this attention mechanism. So as it's writing, these sequences were generated by, it's slowly moving through the corresponding text vectors, the T, the H, the E, the S. And you can really see that as it's writing, for example, as it's writing the letter S, it's looking at the letter S, and it's also looking at the letters before and after it. And this is, you know, obviously for cursive handwriting, this is very important. You need to be you always need to be looking at a window, because you have to know when you're writing a particular letter how you're going to join it up with other letters and how it joins up with the previous ones. And actually, you can visualize this. So, you know, you look at the alignment, you get these kind of curves like this that basically show, you know, what this heat map shows is when it was writing. You know, look at wherever it was at the bottom and go straight up and then go left, and it shows you what text it was focused on when it was writing a particular thing. And it's, you know, it's essentially focused on the thing it's writing with a window, right? And it's important that it has this window because it's using that to make the writing smooth. Okay. Let me see here. Okay, I'll try and get through, I'll get through this next section and then we'll have a break. So that was attention based on location. So you're basically, you're not attending to the input sequence according to what's in the sequence, but just according to the order that it happened to arrive. And that's one particular way of attending to things, right? It's like, imagine if someone gives you 10 objects, and you say, okay, I'm going to look at the third object now, rather than I'm going to look at the green stone, which happens to be the third object. For some types of problems, location is a very good prior, let's say, and handwriting is one of them. But a much more general thing is what's called associative attention, where instead of attending by position, we attend by content. So now you look at your sequence of objects and you say, look, I want to look at all the green stones, and maybe there's one at position 3 and one at position 7, whatever. That's now the thing that you're looking for. So in this setting, we still have the same basic framework. The network outputs some parameters. We get a distribution over places to look. But here, typically, the parameters, instead of encoding as they did before locations, points in the sequence to attend to, they encode a key vector that is compared to all possible glimpses using some similarity function. So you output, if you want to get green stones, you output a vector that somehow embodies or encodes the notion of greenness and the notion of stoneness. And you compare that with all the vectors that you have, all the embeddings you have for the things that you've just been presented with. And the ones that should be closest to your key are the ones that are, you know, that match it most strongly. And typically, that should give you the green stones and not the red bricks. And this is, mathematically, it's very simple. You have a similarity function S. Typically, this is cosine similarity, which really just boils down to a dot product. You're taking dot products between vectors, and if those dot products are high, then these things are similar. If the dot products are low, if they're close to 0, then they're dissimilar. You typically have to, if you want to have an actual distribution here, which you often do, then you have to normalize things. You can do more complicated stuff. So people have done, not just cosine or some fixed similarity measure, but rather a learned one using a neural network or using a linear operator. But either way, you get this kind of, you get something that's actually very powerful. So in principle, association is all you need in terms of lookup. People have built whole computers using nothing but associative recall, associative lookup, because you can search. It gives you this multi-dimensional feature-based lookup. And what I mean, so I mentioned before, you've got green stones. You might have a lookup that said, look, just give me green things, full stop, right? And it might give you back a green stone, but it also gives you back a green brick. Or you maybe only looked for bricks, or you only looked for stones. So it allows you to, if you represent the data in the right way, if you represent the data in a kind of separable way, then it allows you to search for it allows you to kind of fine-tune which things you're searching for and which things you aren't. So it's a very powerful, very flexible method. And the first place that it was really presented was in this paper by Badenow et al., and he's now at DeepMind as well. Neural machine translation by jointly learning to align and translate. And so, again, that can be used for this, and it was used explicitly for this reordering problem in that original paper. So again, here we have a French to English sequence where generally, unlike going from English to German, there isn't quite as much reordering, but there's certain things like the orders of adjectives relatives to nouns. So we have zone économique européenne, sorry about my French, versus European economic area, where we've just got the same words, but they're slightly reordered, and that's exactly reflected here in this heat map, right? That's sort of the cross part of the sword here is the part where it's flipping around these three words, and it's doing this by essentially learning what it can do is learn an internal embedding. So a word like European, it's learned that word is associated with Européenne. They're both kind of mapped together. When it sees one of those in the input sequence, it uses that as the key, and it gets back the other one from the sequence that it's attempting to translate. This is, as I said, this association is a very general mechanism, and so you can use it for example, for speech recognition. So rather than doing what people have done in the past, including the work that I've done in the past, which was more along the lines of attempting to dynamically kind of stretch and compress one sequence into another. And I should say that approach, the sort of more conventional approach to speech recognition relies again on this fact that there's temporal continuity. Basically, the order of the words and the order of the audio match, right? Like you speak the words in order, basically, and so you don't have to reorder in general when you're doing speech recognition, but you can still use this attention mechanism to try to pick out bits of the sequence. So, for example, some part of the sequence that it knows might correspond to the M word at the start of Mary. It's learned how to recognize that, and it can use association to find it, and then it can learn this kind of alignment pattern that's shown here. Yeah, see, now that I've said all this, I'm trying to remember how this system actually worked. Yes, it's learned that similarity. Or rather, it has a fixed similarity measure, the cosine similarity, but it's learned the embedding. So basically what it's doing is it takes in the input sequence. I think in this case it processed it with a bidirectional LSTM network. So it takes these input vectors that represent words and turns them into embeddings, and then it can search those embeddings.
So would it learn kind of the same embeddings for the different words?
Yeah, exactly. And it can work at a higher level than that as well. It can find phrases that translate from one to the other and so on. But yes, it has to. Association is only as good as your representations, right? Like the mechanism for association is simple. Learning the representations is difficult, and you have to do that if you want to be able to search through them in a meaningful way. And here's another very nice example of this use of associative attention. So this was from another group at DeepMind, Karl Moritz Hermann and others, teaching machines to read and comprehend. And the problem they had there was what they wanted to do was take these kind of quite long input sequences, which are drawn from newspaper articles, I believe, and ask them questions. They're looking at kind of general question answering. You get some big chunk of text, and then someone asks you like they give to children, like an interpretation question. That's not the word I'm looking for. But they ask them a question about the text. So in this case, it is identifies deceased sailor as X, and they're supposed to work out who X is. And so X, it turns out, is entity 23. Okay, so it's a little bit abstract. They remove all the names and replace them with these entity markers for technical reasons, but basically what you have to do is guess which entity would be the deceased sailor in this case. And the problem, so in principle, you can do these things just by feeding them into a very big recurrent neural network. You feed in the whole input sequence, and then you ask it the output sequence, the question one word at a time. The problem is that the networks tend to forget, right? They have problems with very long sequences. it puts too much kind of strain on their memory. But if while they're being asked to answer the question, they're able to do associative lookup on the embeddings that they formed when they processed or when another network processed the input sequence, then their range of memory kind of stops being a problem, because they can look up something like sailor, right? They've got some information about sailor. They can use that to look up in the sequence things that are somehow related to sailors, and use that to narrow down, the search for the thing that they're looking for. So to put it in simple terms, if you have this kind of associative lookup, then the length of time that has elapsed between something that you're looking for and now doesn't matter anymore, right? Like if you think about how the human mind works as well, like you see a person walks into a room and they might remind you of someone you saw 20 years ago or something like that, right? As long as that person has stayed in your mind for whatever reason, it doesn't really matter so much how long ago it happened, right? Because you're not having to search your memory by time. You're not having to say, okay, I want you to look back 20 years. Rather, you're searching by content. You're searching by, and I say searching, I have no idea how this is, embodied in the human brain, but it seems to happen very automatically that we see something and it reminds us of something that we've seen before, something that we associate with it. And so there's a kind of a long-winded way of saying that associative attention can give you a much more powerful memory than you natively get from like a recurrent neural network. And that's why LSTM plus attention has become a real sort of workhorse for sequence learning problems. Okay, and I think we should stop for a break there before we turn to introspective attention. We will now resume the lecture, and for the next section of the talk, we will consider what I call introspective attention. So the kind of attention we looked at so far was selectively attending to some kind of external data. So you had an input sequence in one language that you were attempting to translate into another, and you attended to some part of that input sequence. You had an image that you were attempting to classify, and you selectively attended to some part of that image. So it's quite a straightforward form of attention. But as I said at the start, attention doesn't just allow us to pick and choose between, things that we're looking at or things that we're listening to that's coming from outside. It also allows us to pursue one line of thought over another. It allows us to think about one thing and not another. And that's what I mean by introspective attention. And so if you think that as far as a neural network's concerned, or at least as far as a recurrent neural network is concerned, its thoughts are basically whatever is in its current state vector, its current embedded memory, then choosing to look at some part of that memory and not another gives you a form of introspective attention. And once you have this, you can start not only... So another key difference, typically with external data, you're not free to modify it. You're given an image as is. You're not allowed to change that image. If someone asks you if it's a cat or a dog, you can't just draw a cat on it and then say it's a cat. Whereas if what you're attending to is internal, if it's the contents of your own mind, you're typically modifying the stuff you're looking at the same time as you're reading from it. So you can selectively write as well as read, and thereby iteratively modify your state. So it starts to sound immediately a lot more like a computation device and not just a way of looking at one thing or another. And so this was what led me to, and my colleagues at DeepMind, to develop what we called neural Turing machines, which was a form of memory-augmented neural network. So the idea is that we had a controller network, which again could be feed-forward or it could be recurrent. This is doing what a neural network usually does. It's receiving external input and emitting external output. So that's like the top part of this diagram. But it has an extra part of it that allows it to interact with some memory matrix. And it did this via parametric functions, which we called heads. And this was kind of just in keeping with the Turing machine tape metaphor. Don't let that distract you too much. These heads are they're just functions. They're just parametric functions. The parameters, once again, are emitted by the network. So this is a sort of this is a general rule for building things with neural networks. Whatever you want the network to do, you work out a functional form for it, and you get the network to supply the parameters for that functional form. And that way the network can control this operation, whatever it is. And so in our case, we wanted it to control its ability to select portions of the memory and read or write to those things in memory. Okay, so once again, we used a key part of this system was associative lookup. So I mentioned that before, this neural translation paper. Like I said, this thing has become quite ubiquitous. It's used all over the place. We found it to be very important for these Turing machine-like computational models. So we added a few extra, we actually developed this simultaneously with the other paper. We were sort of busy working away on this when the paper came out. So it's one of these kind of independent discovery. And there were other researchers doing similar things as well. We had a few sort of bells and whistles. So we had a key vector, as is usually the case. This thing is now being compared with the content of memory. So basically, as I said, the memory is a big two-dimensional matrix. Each row in the memory is therefore a vector, which you can think of as a memory, right? That's an independent memory. And now this introspective attention is taking some key emitted by the controller network and comparing it with everything in the memory. So it's doing this associative similarity, this cosine distance between the key and the memory to find the memories that are closest. Now, we normalized it with a softmax. We also added an extra thing, which was a sharpness parameter, a beta, which controls the temperature of the softmax, which can kind of selectively narrow the focus. And we did this because we wanted the network to be free to say, look, don't give me the n nearest things to this key, but rather just give me the one closest thing. Because for some problems, you don't want several, you don't want something that's a mixture of, or I should say, these content-based mechanisms are being done with the soft. This is all soft attention in the way that I defined it before. So this thing gives you, this addressing mechanism gives you a distribution, and then you take the expectation of that distribution. So if the sharpness is low, then the distribution is quite blurred out, and your expectation is a kind of a blurred sum of a lot of things. And sometimes that's not what you want. You want to look at exactly one thing, and so then that was why we included the sharpness. It's kind of a technical detail, so I shouldn't spend too long on it. But actually, we thought, we kind of wanted to throw the everything at this and have, well, so actually my original inspiration for this architecture came from the work that I mentioned earlier on handwriting synthesis. And it occurred to me that this attention mechanism was choosing where to read in the input sequence, and it really is scanning like a tape in that case. It's scanning left to right. I thought, well, if I could write, if this thing could modify the input sequence as well, then it would really look like a Turing machine. It'd have this tape head that's moving around and it can read and write. And over time, the Turing machine metaphor got somewhat lost in that associative memory doesn't really fit too well with the whole Turing metaphor. But anyway, that was the origin of the thing. But we also included location-based attention, which was sort of a direct descendant of this, this reading mechanism that was used for handwriting synthesis. And here the idea is basically a shift kernel that says, look, whatever memory you looked at last, move n steps to the left or right or up or down from that memory. And again, the sort of the technical challenge with all of this is easy to say these things in words, right? Find the thing that's nearest to this key in memory, move n steps left or right in memory. The thing that was difficult about all of this was making it differentiable. And this was sort of a design choice, right? All of this stuff could be done without backpropagation, without smooth gradients. It could be done by reinforcement learning. In practice, it just becomes extremely hard. And the reason it's hard is that those types of reinforced style stochastic gradients, the noise compounds when you have many successive steps being performed, all of which are non-differentiable. And so if you've got a system where you're successively reading and writing things from memory, you can see that these, it gets kind of exponentially harder to get a nice gradient through those operations if you don't have, if the operations weren't continuous to start with. Does anyone have a question now?
What's the shift kernel accomplishing that the attention vector is
Association
not?
doesn't. I'll kind of go through that in another slide. It's another way. I mean, in principle, you can do everything with association. It's important to remember that. In principle, there really is no need to have another. But if you think about what you've got on a normal computer, right? You can look things up by date. You can look things up by title. You can look things up like on Google by some sort of association type of thing. Like basically, it's advantageous to have lots of different ways to access information. Is the short answer to that? Yes.
About soft attention, so could you explain again the thing with expectation? Because couldn't you also just read out several things with a certain way
Yes.
to combine them?
Yes. Oh, well, that is what what it does, right? I mean, well, if by combining you mean adding, so you're talking about concatenating. There's lots of different ways of doing this. Right? One thing you could say is like, take the top n closest things and concatenate all of them into one big vector. But there again, that's not differentiable because as the key changes, you get these sharp thresholds where what's in and what's out of the top n changes, and that's. But if you add them together, then if you add all of it together, then suddenly it becomes differentiable, right? You get an expectation. Yes.
So what is originally in the memory, and how would you update your memory by writing back?
I'll come to that in a minute, right? So like at the moment, just say the memory starts off just being a big matrix full of zeros, right? It's empty, and then you can access it through various mechanisms. Location or so that's another thing. When the memory is empty, association-based lookup isn't very useful, right? Because there's nothing there to associate. You can randomize the memory to start with, so that association will sort of work from the ground up. But you can see that it's kind of artificial. What you really want to say is, look, typically what you actually want to do is say, look, I need some blank memory to write to, right? The first thing you have to do is put something in the memory, and you want to do that more like by location, like give me the first piece of memory, or there are actually other ones, like give me the least recently used piece of memory. That's another useful attention mechanism. And so anyway, I think this somewhat answers the question earlier about like what's the point of having, these different mechanisms. Well, what you can think of is that the combination of address mechanisms gives you different modes for interacting with the memory. And in computer programming terms, you can think about these as corresponding to different data structures and accessors. This is a little bit like STL terminology here. If you're just using a key-based lookup, associative lookup, then the memory is really like a map, right? You've got a key and you've got a value. In this case, it's even simpler, right? Because the key and the value are the same. But you can actually you can define, and people have defined attention mechanisms where there's a separate key-value pair. So the thing you use to look up isn't the thing you get back. Rather, it's something that is being associated with that thing. If you can use some combination of content and location, well, the key you can first of all find the start of an array, and then this location-based shift can give you an offset into the array. So you've got some memory of like, give me that list of n things that were that was told to me yesterday, and then give me the third one out of that list by taking an offset of 3. And if you're just using location, then you're kind of just iterating from where you last were. So you have this iterator that goes through something like an array. And we'll see how the network actually uses these to solve concrete problems. Okay, but so to answer the other question about how does it actually modify the memory, so what I've said so far, that's how it finds things. The heads are basically placed at put at a particular place in memory, or to look at it another way, they give you back pointers to something in memory. But then in terms of what you're actually going to do with that memory, well, either you're going to read, and the read operation is straightforward. It's really exactly like these this expectation value, this soft, basically like the canonical kind of soft attention thing, where you take the lookup, the attention mechanism itself gives you a distribution over a probability distribution over rows in the matrix. That's this WI. And then you just multiply that by the content of the matrix and add this up. So you get a sort of expected return from whatever it was that you were looking up. And that's reading. So that's pretty much the same as all of the other attention mechanisms. But writing is more complicated. And I should probably say that in general, learning how to write is really difficult. And that's part of the reason, like these, see this neural Turing machine and the differentiable neural computer that we did after that. These papers are a few years old now, and those models are still not very in all that much mainstream use. And the reason they're not in that much mainstream use is that learning how to write, in principle, makes them more powerful than a system that just has kind of read-only access. But in practice, it makes the learning problem much more difficult. It's really hard to learn to write things into memory and then to read them back as well. It gives you this kind of coupled learning problem. But that's just kind of an aside. But anyway, the way we defined writing, we said basically it's parameterized using an arrays vector and an add vector, where the arrays vector sort of deletes continuously or smoothly deletes information. Essentially, it multiplies it by a number between 1 and 0. If you multiply by 0, then you're deleting. If you multiply by 1, you're leaving what was there. And then an add vector that's just some vector that's added on after the delete. And this was kind of inspired by the long short-term memory architecture, if you've heard about that already, which contains a forget gate, which essentially does this arrays operation. It decides whether or not to get rid of the information, and then this input gate, which decides whether or not to add something new to the contents of the cell. So you have basically a soft form of basically, if the arrays vector is 1, then the write head just exactly says, get me to, and if the arrays vector is 1, and if the attention is completely focused on one row of the memory matrix, then you have this completely clean thing that says, take whatever is in row n of the matrix and replace it with this information that's in my add vector. So at that point, it corresponds to what we expect from a normal computer. But in order to make the whole thing differentiable, there has to be this continuum between doing that and between kind of accessing several different rows in a kind of blurred out way and more or less strongly deleting what's in those rows. Okay, and so, does this sounds awfully complicated, can it actually do anything in practice? Well, we started off with the simplest sequence kind of algorithm we could think of, which is just to copy some information. So we give it an input sequence, which is a whole bunch of these random, binary vectors, or, like it's a vector of size, I can't remember, is it 8 or 6 or something like that of binary numbers. And you get a variable number of these vectors. In this case, maybe it's 20 or something like that. And then after you've seen all of them, you get a little indicator, this little white dot right at the bottom that says, okay, the sequence over now. And then the task is just to output everything you've seen so far. So it's just copy. You just have to remember a bunch of stuff and then write it down. Sounds completely trivial. An ordinary LSTM network can actually do this up to a certain length, right? It can learn how to remember information. What it can't do, where it really falls down, is if you train it to model sequences of up to length 10, and then you ask it to copy a sequence of length 20, it breaks, right? It doesn't know what to do because it's sort of explicitly learned during training that it has to copy, the nth element of the input to the nth element of the output. In other words, it hasn't learned an algorithm, and that's what the neural Turing machine kind of project was all about. It was, can we get a neural network to learn algorithms just with an ordinary end-to-end gradient-based learning? And that's why we're talking about data structures and accesses and so forth. And here it does learn an algorithm, which is kind of expressed in the pseudocode here, which is kind of like the way you would implement copy in a really low-level programming language. So you start off by moving the head to some start location, which doesn't really matter. The memory is empty. It doesn't really matter where you start. As long as you're receiving inputs, you write the input to the head locations. That is, you set the arrays vector to 1, and you write down an embedding that represents this binary vector, which isn't necessarily exactly the same thing as the binary vector, but it's something that the network can sort of decode to that binary vector. Then you use your shift operator to increment to the next row in memory, and then you repeat the process. And you keep doing that until you receive this input delimiter. And then you jump back to the start location, and typically you're going to do that using associative lookup. So you left something at the start. You left a kind of flag at the head of your array such that you could find your way back to it associatively. And then you start reading these output vectors in. So before you were writing, now you're reading. You emit the output, and again, you increment using your shift operator. So it uses these two attention mechanisms in tandem to implement a very simple, just, keep on iterating one step at a time and writing stuff down, then go back to the start, read it back, and copy it. And as I said, the thing that made it interesting was that it generalized. So if we trained it on length 10 to 20, and we looked at what happened at length 20, at length 40, at length 50, I think at the bottom is length 100, it made some mistakes. It wasn't perfect. So these heat maps basically show, they should look exactly the same between the targets and the outputs for training. And you can see they're not perfect. There's a few mistakes. The one at the bottom, for example, I think at some point it misses out a target. So everything is actually shifted along one to the left. But generally, you can see that it's running a slightly imperfect copy algorithm that has generalized beyond the range in which it was trained. That was kind of the interesting part here. OK, so we thought, OK, where can we go from that? Well, maybe the simplest next thing we'd like this to learn is a for loop, right? So let's just take that copy algorithm and say, well, now you don't have to just copy something once. You have to copy it n times, where n is a variable. And again, it basically learns exactly the same algorithm as before, except it learns how to count, to keep this, to store this number n in the memory, and to iteratively decrease it after each step, so that it knows when it's finished and it's emitted all of the data. Now this was a more complicated algorithm it learned, and I might struggle to remember exactly how this one worked. The idea was that there was an underlying n-gram model from which some data was generated, which had n-gram transitions. So like basically, if you look at the binary sequence at the top, you could say given the last 4 values in this sequence, if they say it was 0, 0, 1, 1, there'd be a certain probability of a 0 coming next and a certain probability of a 1 coming next. And you generate from that and repeat, right, if it's a 4-gram. And essentially, the task then is to look at that sequence and work out what the n-gram probabilities are, and thereby use them to predict what's going to come next. And there's an optimal way of solving this problem. There's an optimal kind of Bayesian solution. You start off with a sort of a uniform prior that everything is 50-50. Every transition is equally likely, and then you update that with each new piece of information you receive. And when we trained NTM on the same problem, we found that it wasn't quite optimal, but it came pretty close. If you look at the NTM outputs compared to the optimal ones, so the middle row compared to the top row, you can see that they're a pretty close match. Whereas an LSTM network was much slower to update these probabilities. And those 2 arrows those 2 red arrows at the top represent something important that I'm afraid I cannot remember. It's been too long since this paper. It was something that highlighted the difference between what NTM and LSTM are doing. But anyway, more important than that is that this kind of goes back to what I said about explicit attention mechanisms being good for analysis, good for interpretation. So because we could see exactly what it was looking at in the memory, we could infer the algorithm that it was using to solve this problem. And it is indeed learning a little algorithm, which was that it used specific memory locations to store variables that counted the occurrence of particular n-grams. So it looks at how often it's seen 0, 0, 1, 1, how often it's seen 0, 1, 0, 1, and so on. And it basically just has a look, and that's essentially all you can do with this problem. You store a lookup table, and if you've seen 0, 0, 1, 1 a lot of times and 0, 0, 1, 0 not so many times, then you say, OK, usually I think that followed by 0, 0, 1, there's a higher probability of a 1 than a 0. And it did this by adjusting every time it sees the same. So these green arrows, I think, show the points where it's seen the same n-gram again. And it has adjusted this value in memory. And then it looks up. So if it's used its memory to store the count information for a particular n-gram, then when it tries to make a prediction following that n-gram sequence, it looks up the same place in memory and uses that to determine how likely it is to be a 1 or a 0. I hope that makes some sense to you.
Forgive me for asking, but what is the benefit of doing a model in this fashion rather than learning a Bayesian, the equivalent Bayesian model? Right, I mean, what do you have? Oh, I'm storing counts and I'm doing
The point is that it's generic. So I mean, for this particular problem, there's no reason at all, right? A Bayesian one is strictly better. It's just that, you know, what we have here is an end-to-end system that receives nothing but inputs and outputs. So we don't have to tell it anything about n-grams, Bayesian probabilities, anything like that, right? It just learns that directly from the data. So I mean, all of these algorithms, right? These are all trivial. Copy n times, copy. I mean, you know, they're not difficult algorithms to program yourself or to, you know, to infer. I mean, you could also through some form of, you know, program inference, you could find them quite easily. The challenge, these are more like sort of unit tests to say, well, if we have a system that's completely generic, has no sort of inbuilt bias, or has no, it's not true to say it has no inbuilt bias, but it has no kind of prior information about these tasks, can it still learn them just from end-to-end training?
So that pseudocode you showed on, that's more a representation of what has been learned.
That's my sort of inference of what it's doing. There's nothing.
The model itself.
The model doesn't see that.
Agnostic
It's,
and unchanged
yes.
between these examples.
Yes, exactly. So it's all the same model. It's just, you know, these are just sort of tests of can it learn sort of simple basic algorithms. And, you know, the feeling was if it couldn't do those, then it wasn't going to be. I mean, long term, you know, what you'd like this to be useful for is more like high-level cognition tasks, things like navigation, for example. Like you've walked into a room and there was something that you needed to remember there, and you need to use that later. Those sorts of things. Or for, I mean, there's a sort of notion of a real-world algorithm. So something that sounds really trivial, like you know, tell a robot to put a red box on top of a green box, and then say, like, now put 3 more yellow boxes on top of the green one. That's a sort of simple algorithm, right? And you want it to learn that as an algorithm so that it can generalize, so that if you switch the number of boxes or change the color, it doesn't then need 100, you know, training examples before it gets it right. So it's more of like an issue of generalization than anything else. And it also learned a simple sort algorithm here, where it so the idea here was you gave it a bunch of random inputs and you gave them a random ordering. You gave them a priority, and it had to reorder all of the inputs to put them in the order given by this priority sort. And it did this with a kind of line sort, which, so it didn't learn quicksort. It didn't learn some fancy sorting algorithm. It learned something very simple that worked within the range on which it was trained. But it still was learning how to sort these vectors. Okay, and here's a little video showing like what goes on during training. So this big multicolored thing on the right is the memory, where the size and the color of the squares shows the value of the information in there. So maybe I'll just go back to the start again. And the pink and blue heads are the read and write, the locations of the read and write operations. When they're more or less blurred, that means they're more or less focused on a particular point. It's hard to explain these things as they're running, I must say. So what happened there, this is for the repeat copy task. Once the network is trained, it's at this point here. It now gets a new input sequence coming in at the top now. As that input sequence is going in, the write head scanned down and wrote all the vectors one after another. Then it has to, the read head, the pink one, jumps back to the start, reads through everything in order, sends it to the output, goes back to the start, sends it to the output. And meantime, while it's doing all this, you can see that all these vectors, these numbers in the background that aren't being used for the task are just getting bigger. So the size of the little circle represents the magnitude of the number. And it's basically using those background numbers as a counter, I believe. And then you can see when it's finally finished, it makes this one line at the bottom just really, really big. It makes all the numbers much bigger at once. And that means that it knows when it gets there, it's time to stop. So it's doing all of these things. It's doing iteration, it's finding things with association, and it's learning some sort of termination condition. Okay, and so we then extended this to what we call differentiable neural computers. I mean, people have asked about the name change. It came from, as I said, the Turing machine metaphor was starting to feel increasingly strained because we weren't really thinking of it as a Turing machine anymore. It was much more like take a computer, a real computer like we've got, maybe it should have been called, you know, a neural von Neumann machine. It's not, you know, I'm not entirely sure, but you know, take the computer you've got in front of you and look at all the ways that accesses and manipulates information. How many for these things can we build some sort of differentiable analog that we could feasibly use to train a neural network? And so we added some bells and whistles. We made more complicated ways of accessing memory. I'm not sure. Maybe I'll skip through these a little bit. Like, these details can get rather involved. The overall architecture looked like this. It was still fundamentally based on this idea of looking things up in memory using association was still the most important part of this model. But now it had this extra way of accessing information. One of them was by memory usage. So that's actually quite useful. It could say, give me, basically, I want to write something to memory, so just give me some free memory, right? Which is what you kind of normally do what you're used to doing on a normal computer. You allocate some memory that isn't already being used. And it does this by keeping like a differentiable version of a free list that tells you, to what degree is it using a piece of memory. And this information gets automatic. Every time it reads a piece of information, it can then decide afterwards to flag that as being free, right? If it reads it and it doesn't need it anymore, it can flag it and then reuse it later. This is something that it hasn't really borne fruit yet. Like the point here was that you've got a lot of tasks where you might have a very large amount of information you want to process, but you've only got a fixed size amount of memory. So I was thinking of sort of reinforcement learning or something like that. You're traveling around in a maze. You can't store everything. Your frame rate coming in might be 30 frames a second or something like that. You can't be writing to memory 30 times a second and just keeping it all around. At some point, you've got to decide to keep some things and get rid of others, just for computational reasons, if nothing else. And so I kind of thought it would be nice if you had a way of saying, given a fixed amount of memory, let's be able to actually allocate and deallocate like you can on a normal computer. And so it works. We tested it. It works in sort of the unit tests we designed, but I don't think it's really found a home in real-world applications yet. And the other mechanism that we introduced here was the one that we used to replace. So the temporal shift mechanism in the NTM felt a little bit brittle in the sense that it really relied on the actual indexing of the rows. If you're at row I, you went to I plus 1. And well, for one thing, that feels very unneural, right? There shouldn't be something that really keeps track of an index. You don't know. You're not worried about which neuron you're looking at for a particular memory. And for another thing, it could actually, over time, I think it could lead to fragmentation problems, which is kind of a weird thought. But it sort of forces you to allocate all of your memory in large contiguous blocks of information. So once you start having this more like system where you can dynamically free and allocate things, and you want to have large blocks, then you're getting into operating system design territory, right? Things can get complicated, and we didn't want to design a neural operating system. So the thing we used to replace this location shift was what we called temporal links. So it just keeps track. There's a matrix that keeps track of where you wrote to previously. So basically, anywhere you are in the matrix, you can then jump directly to the next place you wrote to after that, or the one you wrote to immediately before that. So that if you wrote down n things in temporal order, it doesn't matter where you put them in the matrix, you can get back that order of n things. And so this sort of comes back to this idea again. We want associative lookup, but we also, the problem with pure associative lookup is it tends not to store temporal information. And that temporal information that's a very important part of human cognition. Often we'll remember something, let's say, a particular color, a particular item of clothing someone is wearing will remind us of something that someone was wearing before, but then we'll also remember a kind of a window around that earlier memory. Like we'll recall a sequence. So we're recalling both according to associative recall and according to temporal kind of temporal contiguity, let's say. Again, it's just this idea of, like with neural networks in general, more is more. If you can give them more ways to do things, more pathways to process information, more ways to manipulate things, then they can always learn to use some and not use others when you train them. They generally just get better if they're more flexible. Okay, I'm not going to go into these details. It's just too technical. This little thing shows the test we did for memory allocation. So could we give it lots of information such that it had to store things in memory, but it only had a small memory? So basically, it had to repeatedly copy things. We'd give it this little white blob at the top left is an input sequence, and then it has to do this copy algorithm where it copies that and writes it out again. Then we'd give it another one and another one after that without erasing the memory. So it had to learn to free up the memory so that it had space to keep on doing this task. So it's kind of a trivial thing, but it showed at least that it can use this memory reallocation. Okay, and yes, this is the temporal link matrix, which is pretty complicated. In practice, one thing that we were really keen on is, can we use this to process graphs? So I think graphs are like a super general, super interesting kind of data format. So if you think about a recurrent neural network is designed for a specific kind of graph, which is a chain, right? It's a sequence where everything is linked to the thing that came next and linked to the thing that came previously. But generally, there's lots of different graphs we can think of that can be used to represent information. So in this slide here, for example, we can see, well, we've got a London Underground map. That's obviously a graph. There's links and nodes, stations and lines. A family tree is another form of graph where you have the links being different forms of familial relationships. But there's many more abstract things than that you can think about. You can knowledge graph, right? There's a reason that knowledge representation generally relies on graphs, because you have links between entities. You have the notion of someone having been in a particular place at a particular time or something like that. You can define almost anything, any form of relationship you can think of. You can put it into a graph. And so we thought it would be cool to have a model that wasn't just limited to processing sequences, but rather you could give it any kind of random graph and it could operate on it, and it could learn all this end to end. So the emphasis, although the architectures were very similar between differentiable neural computers and neural Turing machines, the emphasis of the papers was somewhat different. Here we were interested in processing more complicated relational structures rather than finding algorithms so much. And so we did a bunch of tests where we trained the data on random graphs. So this bunch of grapes looking thing in the top left is a random graph with random, somewhat semi-localized connectivity. And then the idea being we would give it problems like traversals. So a traversal just says start at a particular node. So all of the nodes in these random graphs had unique identifiers, which are just vectors being fed into the network. And of course, there's identifiers to show which nodes are linked to which. And we would say, well, start at a particular, and the links have identifiers as well, I think, yes. And you would train the network with a task like start at node N, follow link A, link B, link C, now where do you end up? So it's just a traversal in a graph. It sounds really trivial, but actually that form of question has quite important applications. So to go back to the knowledge graph example, there's this whole set of problems in knowledge graphs. You can ask a straightforward question like, who is Obama's daughter? And if there's a link in the graph that encodes that information, it'll be able to find it. But if there's a few levels of indirection, who is Obama's daughter's best friend and like at high school and where were they born or something like that, there isn't going to be a single link encoding that information. Rather, you're going to have to follow a few steps. So you're going to have to do a traversal in the graph. And so finding a general architecture able to do that actually has some real world applications. But so just to demonstrate it, we said, well, look, if we took the London Underground, that's just a specific graph. So we haven't trained this on transport graphs. It hasn't seen the London Underground during training. It hasn't seen anything that corresponds at all to transport or anything like that. It's just completely random graphs. But if it's really learned how to parse graphs, how to manipulate them, how to perform these kinds of tasks, and essentially parsing a graph means getting the whole graph structure in some completely random order, putting it all in memory, and then being able to operate on that memory such that you can use the structure of the graph, if that makes sense. So it's kind of like, in some sense, you're sequencing the graph, but the sequence is random. And now it's just a whole bunch of stuff written into memory that you then have to traverse and find your way around in order to answer the problems. Anyway, in the case of London Underground, the question becomes something like, start at Oxford Circus, follow the central line, then the circle line, circle line, circle line, so on, and make all these steps, and where do you end up? And it could answer those ones no problem. A slightly more challenging kind of well, actually a lot more challenging task is find the shortest path between 2 points in a graph. So really what you want to do is to, solve a shortest path algorithm, which, we know we can do for arbitrary graphs. In practice, it didn't solve the algorithm, right? It didn't find a sort of optimal pathfinding solution. It found something much more heuristic that in a way is more like what a person would do. Like when we analyzed how the network was behaving, it would kind of look, it's being given this, the question, the form of the question is, here's the start station, here's the end station, now give me the route. And it would start at, either end of the sequence and look around a little bit, look a few steps around and attempt to kind of find a way to join them up, which, I mean, is not, as I say, is not unlike what a person might do looking at the same problem. But it certainly wasn't, optimal in any sense. But it could do up to maybe length 5 or length 6, paths. It did a pretty good job. And it could find these routes on the London Underground. Another set of problems that we wanted to look at was inference. And again, this is something that has real world implications for question answering, for knowledge graph and so forth. And so we set up the inference problems. Again, we trained it all on random graphs. The form of the problem would be that you're given an implicit link, which is not stated in the graph itself. So in this case, maternal great uncle has a specific meaning, which is essentially a traversal, right? It's a chain of relationships in the graph, your fathers, mothers, brothers, whatever. I can't remember. But it's never explicitly represented in the graph. It just has to work out what that means. And then so in this, and I should say again, during training, there's no notion of great uncles or grandmothers or anything. It's given completely random labels with completely random links that have particular meanings. But then to illustrate it, we took this family tree example that makes sense to us as people, and we could ask it who is Freya's maternal great uncle, and it can answer by following this inferred chain of relations. And this slide shows, so the analysis gets a little bit more complicated. This complicated slide shows how it does these things, how it reads these graphs. Again, it uses a combination of all of these attention or memory mechanisms that it's seen so far. I think I'll try and simplify things a little bit. Essentially, it gets given the graph in the form, so it's being given triples like Oxford Circus, Tottenham Court Road on the central line. That's what the very top left, that's what the triple at the very top left means. And that's encoded just in some, there's some identifier for Oxford Circus, there's an identifier for Tottenham Court Road, and there's an identifier for the central line that are just kind of randomly assigned. And it gets all of those in order. It writes them all down to memory. So this heat map thing in the middle of the bit with the green squares shows where it's writing to memory. It's very straightforward. What it's doing is saying, give me a blank piece of memory. Now I'm going to write down the next triple from the graph, and so on until it's finished with the whole graph. Then it gets the query, which is another sequence. It writes down the whole query. And then it starts to answer. So the first thing it does, it uses association to go back to the start of the query. And then it kind of gets interesting because then it has to start using this associative lookup for key completion. So giving an incomplete query like from Victoria, follow the Victoria line north, it can look up, it can sort of specify 2/3 of a triple, use that as a lookup, and the thing that will be closest to that is the thing that completes the triple, right? There's only one thing in its memory that has start, destination, Victoria, and line Victoria North, and the complete triple gives you the destination as well. So this is another illustration of how powerful associative lookup can be. You can use it to fill in the gaps of your missing information, and it basically does that successively to solve this problem. Okay, so kind of running out of time now. Another branch, we talked about introspective attention, right? This idea of selectively attending to memory, but there's actually a lot more you can do just with visual attention than what we've seen so far. And so from back in 2015, this was become a very influential paper by Carol Greger and others at DeepMind. The idea was to use Gaussian filters to read from input images and draw to a canvas. So actually this has a feeling a lot like neural Turing machines, but it's more like instead of an abstract memory matrix or a tape that you're manipulating. Rather, there's a piece of paper that you're drawing to, and you have these operations that are that correspond to more like visual manipulations of the data. So more specifically, what you have an attention. Your attention mechanism here is parameterized as a bunch of Gaussian filters that you convolve the data with. They have the filter variance. They have a location for the center point of this grid of filters, and there's a grid stride and an intensity. And the images on the right here show what happens with different settings of these parameters. So like the top one, you can see, because of the grid stride has been made relatively small, so like in some sense you're cropping out a small part of the image, although I should say that this is soft attention again. So none of these operations are hard. There's no like hard cutoff. There's rather like a soft convolution between a filter and an image, so it's all differentiable. But basically now you're focusing on the center of this letter 5. And it's quite blurry because you've got quite a high variance, which is shown by the thickness of the green line. This other one is more like kind of neatly cropping out the 5 itself with quite a low variance, so it's sharper and so forth. And this is a visualization of what happens when you use draw to, so in this case it is, this shows how, so the way draw was kind of used, it was trained like an autoencoder, like you give it an input image and it's able to look at that. It's a variational autoencoder. I won't go into the details of that. Maybe you'll hear about those elsewhere in the course. But basically it sort of has the image in front of it and it builds a compressed representation of that image, and then from the compressed representation it builds up this internal canvas that it's going to use to reproduce the image. So this first animation, whoops, sorry. Huh. Yes, the first animation shows how it attends to the image, and you can see that it sort of starts off looking at the image as a whole. These things are always too fast. We just slow down all our videos. It starts off with this green square that shows its attention looking at the image as a whole, and then it shrinks it down and kind of traces out the image, like a stroke, which is very interesting. And then it kind of does the same thing when it generates, right? So the drawing, the actual procedure used to draw to the canvas, it does it in something that looks like a person following a stroke. And this is what it looks like when it generates street view house numbers. And also, these are generated images. They're very convincing. I remember when Carol first, demoed this, everyone was really quite speechless. Compared to generative models now, perhaps it doesn't look so striking, but at the time it was really quite ahead of its time, and it showed how these generative models could be used to really create things that you can't distinguish from real images. And in this case, it was learning this kind of right to left sort of sweep through the data. So this sort of comes back again to the thing I said at the start about turning static images into sequences. In draw, everything is a sequence. It's a sequence of fixations. These Gaussian convolutions are used to kind of read or process the image, and then in parallel, a sequence is used to build up your reproduction, your reconstruction of the image. Okay, and I think we're kind of out of time. I think maybe I'll skip this last slide, which was an extension of draw, which kind of went beyond just having this Gaussian grid and considered more general affine transformations, rotations and scales and things like that. But it's the same basic principle. It's kind of like a specifically visual form of soft attention. Here's a demo of it in action. It's kind of nice. I mean, this shows how it can rotate images and transform them in some kind of nonlinear way. I think there's a. Oh yes, and he did it in 3D as well. So this is 3D MNIST now. It's kind of ridiculous the lengths we go to keep on using MNIST for all of our all of our problems. Okay, and that's end of the lecture. Just to summarize, selective attention is it's important for people, it's also important for neural networks, and I think its importance will only grow over time. These systems get more and more sophisticated. I expect to see more attention built into them. They always have some kind of implicit attention, and you can kind of query this, you can analyze this just by looking at the sensitivity, but you can add explicit attention mechanisms on top. You can have stochastic ones that are kind of reinforcement learning, like where you have just a stochastic sample over your next glimpse or attention. Or you can do the soft attention, which is differentiable and can be trained with backprop. And you can also use attention to decide where to write as well as where to read. So it becomes something that allows modification as well as access. And I think maybe the last and most important thing is there's lots of different kinds of attention, right? We've seen content, we've seen location, visual, temporal. There's lots more, and I think more will keep on appearing. It's still quite a fertile area of research. And that's the end of the lecture. Thank you.